Okay, good day, class. This is our first session for our coverage for the second exam, which would cover up explosives, gunshot residues. We'll also be discussing about uh, toxicology, blood, semen, and DNA analysis. So for this session, I'll be presenting to you an introduction about explosives. So also, I will be sharing to you a video with regards to what you need to know about explosives. So, what are explosives? The history of explosives. And soon after, on the succeeding sessions, we'll able to discuss more about explosive types, effects of explosion, and analysis of explosion. So, let me share the video. And I hope that you would be able to take down notes while watching the video.
So let me now introduce you to our speaker of today, which is Brecht Egela. Brecht is an organic chemist by training, and he obtained his bachelor degree at the University of Hasselt. After that, he also obtained a master and a PhD degree at the KU Leuven. He has currently a position at Janssen Pharmaceutica, where he works as a senior scientist in process safety, and he is also a volunteer in the company's fire department. Explosives are one of Brecht's great passions in life, and he enjoys sharing that knowledge. He has been giving training in explosives to firefighters, civil protection, and law enforcement for almost a decade now. He is also a lecturer for the Adviseur Gevaarlijke Stoffen postgraduate study at the University of Antwerp.
You can turn matter into other matter passions in life. I'm a chemist, and chemistry has been my number one interest all my life since I was a little boy. But love starts somewhere, and for me, love started with explosives, my love for chemistry. So as we are walking through this beautiful realm of these powerful molecules, keep in mind that I'm not only trying to share you a passion for explosives, but also for chemistry itself. Chemistry is truly a power of transformation. You can turn matter into other matter or matter into energy, and there is no better way to show this than to show you how explosives work for dramatic effect, of course. So today, I will teach you about some of the explosives. I'm a chemist, not a historian. So you'll see I'll focus a lot on the chemistry. We're going to use history more as a kind of guide to show us the different portraits of the molecules of explosives as we will see on our journey. So what we're going to talk about today, I'm going to show you different types of explosives. We're going to start at the very beginning. What is an explosion? Then we're going to go to the grandfather of all explosives. That is, of course, black powder or gunpowder. We will then see what Nobel, Alfred Nobel, better known for his Nobel Prizes, what he had to do with explosives, a great deal, as we will see. We will then go into some darker parts of human history, being World War I and World War II, and to then go on into a more recent realm, the current technological innovations that are taking place in the explosive science. And at the very end, because of course, unfortunately, every presentation about explosives isn't complete without some very recent, let's say, points of attention, like terrorism, of course. So we will end on a maybe sadder note, let's say. Explosions, first of all, what is an explosion? This is an explosion. What you can see here is an explosion of about 1.5 tons of gunpowder, of black powder. So hope that made you a bit made you a bit more awake. So what is an explosion? An explosion is, in essence, a very rapid release of energy, so fast that it cannot be dissipate it to the environment in an easy, slow way. It has to go so fast, it generates a pressure wave, usually also a lot of heat. And that pressure wave is going to cause usually damage to the environment. Here we see the explosion has shattered the house in which it was taking place. Fragments are strewn around. There's a shock wave taking place. Very dramatic, of course. This to me is an explosion. There are many ways in which you can cause an explosion. You can cause an explosion using obviously chemical means, which is what we're going to talk about today. You can also cause an explosion with purely physical means, for example, a pressure explosion from overfilling a vessel, for example. You can, of course, obviously also create an explosion using nuclear fission or fusion. I won't talk about that today. That is more the realm of the physicists. And there are also some more exotic things, like, for example, solar flare explosions. That is for sure not my expertise. We won't be talking about that. No, we will be talking about the chemical explosives, obviously. And as I said before, let's start with the oldest of all explosives, the venerable grandfather of all explosives. And I can't put it in better words than, well, Satan himself in Paradise Lost. The deep shall yield us, pregnant with eternal flame, such implements of mischief as shall dash to pieces and overwhelm whatever stands adverse. You see, Satan needed to fight the armies of heaven, and to do that, he needed very powerful weapons, and he made gunpowder, of course. He still lost, by the way. But this already kind of shows you how gunpowder was perceived at the very beginning, more of a devil's tool, particularly in the West. However, gunpowder did not find its origin in the West. It was invented in China, actually, already in the 9th century. Back then, maybe perhaps very ironically, the people who first developed, let's say, the initial form of gunpowder were Taoist alchemists. And they weren't looking for a weapon, they were actually looking for an elixir for immortality or eternal life. So you can understand it's very ironic that instead of eternal life, they found an efficient way to end lives. Taoism, for those who may not be familiar with it, is an old Chinese religion. I think it's mostly known here for its association with the yin yang symbol. So I hope that whenever you see the yin yang symbol now, you'll be thinking about gunpowder and we're thinking about me. So these guys were very interested in the essence of things. And that actually was a boon to them because they wanted to purify everything. Whenever they wanted to make a new concoction, they needed to purify the ingredients first. And by doing so and mixing things in various proportions, they came to the fire drug, a mixture that produced flame, vigorous flame, and also caused a slew of accidents, of course. Obviously, they took a great interest in this. And it's maybe some kind of a misconception. Sometimes you hear that the West is the one that weaponized gunpowder. This is absolutely untrue. The Chinese were far ahead of us. They already used it in warfare in the 11th century. That's almost more than 1,000 years ago. The first gunpowder weapons were relatively crude. On the left-hand side, it's here, you can see a fire lance, actually a very rudimentary device, simply a spear with what's basically a piece of firework attached to it, filled with gunpowder. You would light the fuse and stab down at your opponents, usually when they were attacking your walls, whilst shooting forth flames of gunpowder at their face. Very intimidating. In the middle, we see another beautiful weapon, aptly named the 9-arrow heart-piercing, magic poison thunderous fire eruptor, a sort of arrow-launching proto-gun in a sense. We're going further with these, let's say, proto-missiles, which were actually just overblown pieces of firework in a sense. But keep in mind, and we will see this also later when we're looking at the more Western implementation of gunpowder. For the medieval mind, gunpowder was something incredibly intimidating because not just the fire, but especially the sound. You have to keep in mind an exploding piece of gunpowder at that time must have made a sound that you can only ever have heard during a thunderstorm. It was magical, it was intimidating. That's why it was also a very powerful weapon of war. During a famous battle in China, a naval battle in Lake Poyang in the 14th century, they made incendiary devices, based on gunpowder that were aptly called no alternative. I really love the Chinese and their and their noms for weapons. Um, in the West, actually, gunpowder only arrived around the 13th century. And as I've said before, it was mostly the domain of the devil. You see here on the right-hand side a depiction of Bertolt Schwarz. Bertolt Schwarz is sometimes called the inventor of gunpowder in the West, but there's not really a consensus whether that man was really a real figure or more like a mythological person like Robin Hood or something, and more a kind of persona or personification of general people in the West that were busy weaponizing and working with gunpowder. Here you can see him loading a cannon, and you can see clearly Satan, the devil, whispering the secrets of gunpowder in his ear, because to the medieval mind in the very beginning, gunpowder was a tool of the devil. It smelled of sulfur. It caused tremendous noise that no man, and wielded power that no man should have. And of course, these gunpowder weapons were, in a sense, incredibly dishonorable. Any simple peasant with a gunpowder weapon could kill a knight or a nobleman. Another important figure in Western culture regarding gunpowder is Roger Bacon, probably familiar to most. He was for sure real, and he's probably the first one who really studied gunpowder to some extent in a proper way. He wrote it in his book as well, where he found the gunpowder to be so powerful and dangerous that he wrote down the formula for gunpowder in a kind of cryptical way. Here, translated rudimentary as 6 parts of saltpeter, 5 of young willow ash, which is charcoal, and 5 of sulfur. Now, this formula is definitely suboptimal, as we will see. But he was very afraid of it nonetheless. He wrote literally in his book, "This secret is a key which opens and no man shuts." As you have seen, once gunpowder opens something, it's probably never going to shut again. Another important work in Western culture regarding gunpowder is the Liber Ignium ad Comburendus Hostes, very nice old manual which contains all sorts of incendiary weapons. Literal translation of this book is then also the Book of Fire, to set fire on your opponents. So, very nice. Um, in fact, the true weaponization of gunpowder in Europe itself only started around the 14th century with rudimentary gunpowder weapons, such as the ribocot, which you see here, a sort of multi-barreled gun used to shoot from short range. We, of course, had the cannons and the bombards, the first cannons. It's important to note that the technological formation of innovation of cannons went hand in hand with metallurgy, because the problem was, I mean, gunpowder was known for a long time, but the true cannon took a while, because it's very hard to control the energy of gunpowder sufficiently to launch a projectile without also blowing up the gun in which it is in. That really required a higher level of understanding of metallurgical principles, which took until the 14th century to really develop. But once there, it progressed relatively rapidly. And cannons and gunpowder also dramatically changed the way warfare was done in medieval ages, especially siege warfare. Cannons were very powerful and could smash down walls. A good example is the siege of Constantinople, where perhaps one of the first artillery barrages in history was done by the Sultan Mehmed. So we also see down here some rudimentary firearms. The first firearms actually resembled more like a hand cannon. It was operated by 2 people, one holding it and the other lighting the fuse to shoot the cannon, basically. You see here a British musket from the 18th century. So the 18th century, or before we truly had the typical muskets that we know. And to quote the poet Tom Carlyle, gunpowder made all men tall, in the sense that you didn't need to be, you could be a knight, a nobleman trained in the art of war for all your life. A simple peasant with a gun could kill you in the blink of an eye. So, dramatic change of warfare thanks to our beautiful gunpowder. It wasn't only used in war, although that was certainly the first application. From the 17th century on, it was also used for civil projects, like, for example, blasting of bridges, making rivers or canals. In fact, one of the greatest engineering feats of the 17th century the Canal du Midi in south of France to connect the Atlantic with the Mediterranean Sea was actually made, well, partially or mostly thanks to gunpowder as a demolition material. It's now a UNESCO heritage. It's still there. You can go and visit it. But how do we make black powder? Because I know that's what you really want to know, of course. We can have a look at the Liber Ignium and see how to best burn our enemies. There they give a very old formula: 1 pound of sulfur, 2 pounds of grapevine charcoal, and 6 pounds of saltpeter. This is not really the optimum formula. The optimum formula is more along these lines: 75 weight% of saltpeter, 15 weight% of carbon, charcoal, and 10% of sulfur. You may wonder, okay, but what do these ingredients really do? So each of them has an important role to play in the final mixture, because black powder is not a single compound. It's a mixture of different components that each have their part to play. Probably the most important one is the saltpeter, or potassium nitrate is the more chemical name. This is the oxidant. This is actually the compound that, in a sense, delivers the oxygen for this very rapid combustion that is the ignition of gunpowder. Now, saltpeter was actually known for a very, very long time. You can find it in natural deposits, especially in areas where there's soil that is very rich in nitrogen, because nitrate is one of the ways in which it's found and made in nature is by bacterial action on nitrogen compounds, like, for example, ammonia or urea. Um, and when they produce the nitrate is quite soluble in water. So in parts of the world where there's a lot of rainfall, like for example in Europe, the nitrate will be washed away. It will be difficult to find the nitrate anywhere in a place where you can have rain. Um, in other parts of the world, like India and China, there are in some parts of the country long periods of drought, so with no rainfall. And in this arid climate, the saltpeter can rise to the surface and actually crystallize out and can be found, for example, in caves and so on. In Chile, there's even a deposit called Chile saltpeter, which is sodium nitrate, which you can convert into potassium nitrate easily, which actually one of the main sources of nitrates up until the First World War. So one can obtain it in nature as deposits. One can also find it, for example, in basements and other areas where there's no rainfall, but still plenty of nitrogen-rich soil. A very good type of soil, for example, is the graveyard. Corpses are a great source of nitrogen. So again, very beautiful poetry in there somehow to make a weapon from the dead. However, here in Europe, natural deposits are a bit more rare. Luckily, the medieval mind was very innovative, and they made niter beds. Niter beds are a sort of artificial way of producing the ideal circumstances for bacteria to grow and to enact their magic upon the nitrogen organic material and make the nitrate. They're basically compost heaps that you would protect from the rain and leave for a year or two. You do the bacteria to do their work. It's very important that manure is present, so excrement from animals or people, and very important, urine. Urine is a critical component. Urine is rich in urea, as the name implies, which of course has a lot of nitrogen in there. So people making niter beds were advised to sprinkle it daily with urine. And apparently the best urine came from regular drinkers. So somebody who really liked wine was a great contributor to these niter beds. At some point, the king of England even obliged his subjects, whoever was able, whoever had land, to have niter beds and to give their potassium nitrate to the king for making gunpowder. So if you have a big garden, lots of manure and a full bladder, you may produce your own strain of potassium nitrate. The oxidant. The fuel then, if you have oxygen for combustion, you also need a fuel. The fuel comes mostly from carbon. Charcoal, as you know, is pure carbon, like the same one we use to light our barbecue. Very simple. The old way of making it is basically combustion of wood under very oxygen poor conditions. So you really you create these you can see above there, like this black charcoal, very typical. So this was easy and cheap to make. The last ingredient is sulfur. Sulfur is a binder or catalyst. You can make sort of black powder or gunpowder using only potassium nitrate and carbon, but to really get it sensitive enough to get this fast burning action, you need a sort of binder, a catalyst, and that is where sulfur comes in. Sulfur fulfills this important role of lowering the barrier for black powder to ignite and giving it also a better consistency. Now, sulfur can also be found in nature, either as pure deposits, sulfur deposits, as you can see there, or as minerals such as pyrites, which you can then reduce to pure sulfur. So you can see black powder is nice because it can be literally found in nature, its basic ingredients. It, of course, needs to be purified if you want to have a good powder. But that's why it was quite cheap. Now, now that we know how to make it, you may wonder, but why does it work? Why does black powder work? If we look at the very beginning, what I was telling you about explosions, we need a fast release of energy, very fast. The energy will come from the chemical reaction. So obviously, the chemical reaction needs to be extremely fast as well. Um, Now, there are many ways in which you can have a fast and a slow reaction. For example, if we would light a match, we would burn up the wood slowly. There's a lot of energy being released there in the form of heat, in the form of light, but the release is slow. So a candle or a match in this case would not be considered explosive. However, if you would take the same uh, fuel, let's say, like wood, you would powder it, make it very fine. So there's a lot of surface and mix it with oxygen, for example, by blowing it up into the air, creating a cloud. You have a very intimate mixing of the reagents. In this case, fuel, basically wood or wood dust, and oxygen from the air. By creating an intimate mixture and a lot of surface area, when you then ignite this, you will release all that energy in a short time frame, resulting in what would be called an explosion. This is the principle of dust explosions, for example. That is why wood dust, why a piece of wood won't explode, but if you would ground that piece of wood up to a fine dust, disperse it in the air, so mix it very well with oxygen and ignite it, you would get an explosion, as you can see to the right. So it's important to get this intimate mixing, and that is exactly what is also needed to make the gunpowder. If you would just take potassium nitrate, sulfur, charcoal, all just throw it together and try to ignite it, nothing much would happen. You need to have an intimate mixing. There are a couple of ways to do that. This is the beautiful artisanal method. You basically grind all the components together in a sort of bucket or a mortar and pestle. Obviously, doing this with dry material is probably not going to be your best day. So what one did was you would add some water to it, make it moist. The water acts as an inhibitor in a sense. As long as it's wet, it's difficult to ignite. So you would grind it while still wet. This would give you chunks of gunpowder, which would then be sieved. See this man over here doing it? He has a sieve because it's important for a good burning rate that the particles are not too small, neither too big. Too big particles will burn too slowly, which is not good. Too small particles, however, they burn too fast, which is also not good depending on the application. If you want to build a gun, for example, and your gunpowder burns too fast, the pressure will rise so fast in your gun that there's a good chance it will simply explode in your face. So you need to have an optimal grain size, and that's what the sieve was made for. So they would basically rub the wet or still moist black powder or gunpowder through the sieve, making grains of a particular size. Now, this is the artisanal way, how it was done for a long time. Obviously, at some point, industry takes over, and we have these industrial mills where basically the components were waltzed together using these huge stone and later metal discs, basically weighing several tons. They would waltz over the components, mixing them intimately while still wet, of course, into a kind of hard chunks that would later be broken up and sieved. Obviously, this was rather dangerous, and every now and then a gunpowder factory that also went up in a big bang. Here you can see a artist's impression of an explosion of a gunpowder storage in the 17th century in Delft. So gunpowder manufacture has always been fraught with danger and the risk of explosions. That's why they were also at some point also usually far away from any inhabited cities or dwellings. Very good. We have our intimate mixing for a fast reaction, but we also need to still produce this energy. And I've already kind of lifted the veil on this one. If you remember, from basic fire training, our fire triangle for combustion, that typical exothermic reaction that also generates gas. We need an oxidant, ignition, and a fuel. These components, of course, I've also already told you that in the gunpowder, the oxidant is, of course, potassium nitrate. The fuel is the carbon and the sulfur. And so also something interesting also happens here. Because the oxygen, in a sense, is coming from the nitrate, we don't need air. In other words, gunpowder will also burn perfectly fine in a vacuum, for example, without any air present, or in an inert environment. So you cannot extinguish gunpowder by taking away the air, because the oxygen is already in the mixture itself. Now, the ignition part, and this is, I guess, basic thermodynamics. You have all these components. They have a high energy content, especially the nitrate. They want to turn into other compounds like carbon dioxide, carbonate, sulfates that have much less energy. To do that, however, they won't do it spontaneously. They need a kind of a kick. They need a little bit of an ignition. Right? They need to conquer this little energy barrier. They need to jolt it with a bit of energy, enough to get it started, and then it will go all the way to all these low energy products, releasing heat in the process. This activation energy is the ignition, and usually it's going to be in the form of a flame, a fuse, or a spark. What you also see is that actually gunpowder, in a sense, is not a terribly efficient propellant, in the sense that a lot of products that are being produced are actually salts. It's not only producing gas like carbon dioxide and nitrogen gas, it's also producing these salts, which in fact don't really contribute to the propelling force of gunpowder. They are also responsible for the typical, and you saw it also in the very first movie I showed you, at the typical white clouds you see when there's a gunpowder explosion or combustion. And that's because it also generates salt products, and they're kind of dispersed into the air like smoke. We will see later that the newer propellants, they don't generate smoke anymore. They don't generate any salt products. But our friend gunpowder does, giving this beautiful white smoke. Now, black powder is a low explosive. What do we mean by a low explosive is actually an explosive that when it combusts, when you initiate it, it will propagate. Meaning, as you see below here, if this would be a stick of gunpowder, you would ignite it here, it would start burning, the reaction would start, and it would propagate further on until there is nothing left. In other words, you can actually define or observe a speed. How fast is the burning rate? How fast is this reaction front proceeding through the material? And for a low explosive, of which gunpowder is a typical example, but there are many others, this speed is subsonic, so slower than the speed of sound. This has some effects on what kind of damage it can do, for example. For example, gunpowder, for that reason, cannot explode without some kind of confinement. If you would have a heap of gunpowder on your desk and you would ignite it, you would get a pretty impressive gust of flame, lots of smoke and heat and so on. But you won't get a true explosion because the gases are generated at a speed that's still too slow to cause a shock wave. The only way to make it explode is to confine it, to put it inside, for example, a closed tube or a closed sphere or something like that, like a missile. There, the gases can't escape, the pressure will build up, and at some point, the container will just explode, giving you your shockwave. So important to remember, low explosives require confinement to explode. Does it mean that they are less powerful? Yes, but therefore not necessarily less useful. Because they are slower, they are also more useful as propellants. You can use them to propel rockets, propel bullets, something that the more quicker and the faster explosives, which we will see later, won't be able to do for you because they simply go too fast. So low explosives are sometimes for that reason also called propellants because their prime function is to propel forward objects. Here we see an example of gunpowder being lit in the open to make art in this case. You see no explosion, simply a very rapid combustion. That's because it is a low explosive, of course. Now you're already thinking probably, so that also means there must be high explosives, right? And you are obviously correct. Up until now, low explosives, gunpowder was the explosive, the only explosive known for a very long time until the 19th century. And in that century, a Italian scientist by the name of Asciano Sobrero was working on some pretty interesting stuff. He was trying to react glycerin, which is a byproduct of soap manufacturing, with a mixture of nitric and sulfuric acid. He obtained an oil that was insoluble in water, which is peculiar for him because glycerin dissolves very well in water. So he decided to isolate it. He also noticed that it gave strong headaches when you ingested it. Keep in mind, this is the 19th century. We didn't have UPLC or other fancy analytical methods, so people tasted what they made. Um, he did also note that when you heated this solution, you got a violent explosion with a force he had never seen before. And as things went in the 19th century, what he did then was immediately call your friends, your scientific friends, and say, look what I made. They would go to the lab, and as he beautifully describes in his paper, he made it explode again and basically caused many a tear and many a wound in the face of his friend. But also typically 19th century, perhaps, instead of being disheartened, he was very enthusiastic and published his results. He, however, did not really give much more thought to it. He shared his invention, he shared his findings with some other scientists, but he did not exploit it himself later. Unbeknown to him at that time, he had actually discovered the very first high explosive in human history, namely nitroglycerin. Nitroglycerin, which by the way also acts as a medicine, because the reason why it gives strong headaches is because it makes your blood vessels open when you take it. So it's actually a good medicine against angina pectoris. Unfortunately, also maybe a bit of a sadder anecdote. To test this property, again, we're talking about the 19th century here. People, they gave it to a puppy who, after severe convulsion, died from massive hemorrhaging, which they also documented, of course, 19th century style. So the first high explosive in history had been discovered, nitroglycerin. Now, what is a high explosive? This is important, of course. A high explosive is capable of detonation. Detonation, we've talked before when we were talking about gunpowder, about the deflagration, about the reaction speed that propagates through a material at a speed lower than the speed of sound. For a high explosive, for a detonation, this speed is actually supersonic, so faster than the speed of sound, meaning the rate of, it's not really combustion anymore, but decomposition is the better word, is so fast, it's faster than the speed of sound, meaning that you won't even need confinement anymore. The inertia is so big that the energy is really so fast that you will get a shockwave in any case, even without confinement. If you have nitroglycerin, as a liquid, it's a bit difficult, but if you have a solid high explosive, for example, you would have a heap on your desk and you would ignite it or initiate it, it would detonate, it would explode. You would get an explosion with a shockwave, and it would be an unfortunate day for you. Um, since this velocity, how fast this reaction front is going, is so important, it's actually a figure that's used to estimate the power of an explosive. It's called the velocity of detonation, abbreviated as VOD. The higher, the faster the explosive usually means the more powerful. We'll see some examples later. Here we can see, for example, an exploding stick of dynamite taken with a high-speed camera. And you can see that the reaction front is already here and the gases still didn't really have time to expand completely. That is typical of the extreme speed of high explosives. Here we see an example of only about 100 grams of high explosive unconfined in a plastic bag next to a tree. And you can immediately see the results. Shockwave, this ripping action, very typical for high explosives. This ripping action that they have, because of the formation of the shockwave, a true shockwave with high peak pressures, this is called brisance. Brisance means the property of a high explosive to rip apart whatever it is in contact with. We can see a beautiful example here. This is an experiment where a person has filled a piece of tubing, metal tubing, with first a low explosive, like gunpowder, exploded it. What you see is, of course, the tube is closed and the pressure builds up, it blows apart, and you see that the chunks, the pieces of pipe are relatively big. You could, reasonably even reassemble almost the tube in a way. They did the same thing, but with high explosive dynamite. You see, the damage pattern is totally different. All these pieces of metal are warped beyond recognition. There are many small fragments, and you can't see it in this picture, but many other fragments were simply not found. This is typical for high explosives. They rip apart. They don't just give a gentle, in a way of speaking, explosion. They rip apart with whichever thing that they are touching or are in contact with. This is also a way, by the way, how you can identify post-explosion whether you were dealing with a high or a low explosive. So that is the way that explosives are classified. Low and high. Low explosive deflagrate. They have a slow speed of propagation below the speed of sound. And the high explosives have a high speed of propagation above the speed of sound. They detonate. One then can make a further classification between propellants and pyrotechnics like fireworks. The high explosives, however, are classified further in classes that are related to their sensitivity, not power, but sensitivity, meaning primary explosives are very easy to explode, secondary are much harder, and tertiary explosives are very hard to explode. We will see why this is important later. But let's go back to our good friend nitroglycerin. Now, nitroglycerin is a liquid explosive, has a melting point of around 13 degrees. It's totally insoluble in water. It's actually extremely powerful, even by today's standards. Has a velocity detonation of 8,000 meters per second. Now, to put this in perspective, this would mean that if I would have a tube of 8 kilometers long filled with nitroglycerin, and I would detonate it on one side, it would have reached the other side in 1 second. So you can imagine it can traverse 8 kilometers in 1 second. What kind of energy release rate must be involved in this molecule? It's actually, contrary to popular belief, quite insensitive. And the pure material is actually quite insensitive. You shouldn't beat it with a hammer, but you can definitely move it, transport it. You can even shake it gently. That's not a problem. The problem arises when it's impure, when you have traces of acid, for example, when after the synthesis it is not purified properly, then you might have a very dangerous compound on your hands that can explode even by the touch of a hand. How is it made? Well, you only have to look to Sombrero's original experiments by the nitration of glycerine, which is a byproduct of soap manufacturing. It's a very simple reaction, as you can see here. Also a very cheap compound for that reason. We see here how it was originally done in one of Nobel's factories. And this is, to me, every time I see this, a beautiful picture. Rudimentary process safety, there's so much to explain here. But what's important to know is the nitration of glycerin is extremely hazardous. The reaction itself produces a lot of heat, so the temperature will rise of the reaction mixture. If it reaches above a certain temperature, it will explode. So it's very important that when you're adding the glycerin to this mixture, you do it slow, and cooling. You have to cool very well. Otherwise, your plant will go up in a big explosion. Now, keep in mind, we're talking about the late 19th century here. So we didn't really have computers or anything like that. So it's all to be done by hand. So what you see here is actually an operator. He's making nitroglycerin by literally opening valves and slowly adding the glycerin. You have to keep an eye on the temperature at all times. If the temperature rose, you have to stop immediately. If the temperature rose too much, you have to dump the contents of the reactor into ice water. If you made a mistake, it would be his last. So what did they do to improve safety? Also, please note the man's beautiful outfit. We don't dress operators that anymore. A beautiful bonnet. Shame. This interesting piece of process safety here is a one-legged stool. It's a chair with only one leg. The idea behind that being, if you have to dose glycerin to a big reactor, it takes a long time. So there's always the everlasting temptation of sleep, which of course would be the last thing you ever did. So they invented this one-legged stool, which is if you would fall asleep, if you would nod off, you would fall off your stool and wake up. So rudimentary process safety at its best. Now, there was a small problem. Well, there were a couple of small problems. First of all, nitroglycerin wasn't very popular. It was dangerous, but also it couldn't be reliably detonated. It was you could try to light up with a flame, but it would just burn. You would have to burn it in a bit of a confined environment, so the heat could build up until it really would detonate. And even then, it didn't always work. It wasn't really practical to use for that reason. You couldn't just put a fuse in it and make it explode. It didn't work that way. So the question didn't arose to many people, except for one. Alfred Nobel. He actually made nitroglycerin into a viable explosive by inventing the detonator. And yes, this is the same Nobel that is now the, let's say, the spiritual father of the Nobel Awards. In fact, the Nobel Awards, all that money is actually provided by his explosives industry, dynamite. So whenever you see Nobel Prizes again, you will think of me and dynamite because that is what it's all based on in the end. But his invention was quite remarkable. What he did was he devised a sort of device, a detonator, that could be ignited by a fuse where you had a small charge of black powder in a small tube, so a confined environment, which if you would ignite it would cause a small explosion, and this small explosion could reliably initiate nitroglycerin. You could make this happen with a fuse, so a flame, or later on even with electricity. So a small glowing wire would ignite the black powder, which was reliable, which would cause a small explosion, and this small explosion would then set off the nitroglycerin itself. He patented this in 1864. This is the original patent of Alfred Nobel, and this would be the start of his empire. Because what he invented, in a sense, or discovered perhaps, was the explosive train. Like with black powder, to ignite or to detonate high explosives, you need to set it off. You need to give it a jolt. A simple flame is usually not enough. You need to set it off in some other way. And better so, because if you want to make a bomb, for example, you want to have a lot of explosive usually. If all the explosive will be very sensitive to ignition, it will be very impractical to use, very dangerous. So what does the explosive train basically mean is you're going to use a small amount of a sensitive explosive, something that's easy to explode. For example, in Nobel's invention, black powder, and you're going to use that energy, that small jolt of energy, to set off the next charge, which could be your main charge or an intermediate charge, which will then generate more energy to, in the end, detonate your entire block or your entire bomb of high explosive. And that is also to this day how we explode high explosives using a detonator. Of course, the modern detonators look a little bit different. They also contain high explosive. You can see the two varieties here. You either have one which still work with a sort of rudimentary fuse, where you also reach some sort of black powder, and you ignite and you detonate it, or of course the very common electrical ones. It's better to control. You basically have a heated wire that heats up because of the electricity that ignites a charge of black powder on back in the days. Nowadays, it's different, more reliable components, which will make a flame, the flame which will set off the sensitive explosive in here. So you'll be basically using sensitive explosives to set off the less sensitive explosive. Nobel started with, oops, a bit too fast. Nobel started with black powder, but later on, a jolly fellow called Johann Kunkel von Löwenstein discovered a peculiar compound called mercury fulminates, a mercury salt that is incredibly shock, friction, and spark sensitive, and also sensitive to flame. It's also highly toxic. It was discovered already in the 17th century, but considered no more than a curiosity. Later on, Alfred Nobel caught on to this compound because it was much more powerful than gunpowder, and he used it in his first primary explosive detonator. The physics behind it are a little bit more complicated. What's happening with this primary explosive here is basically, in this case, a small energy like a flame or a spark will cause this material to combust, so it makes a flame. But the property of this primary explosive, which is, I mean, there are others like it, typically for a primary explosive, this flame will very rapidly propagate with minimal confinement into a detonation wave. So very powerful, very fast wave. And that is what makes mercury fulminate so interesting, and has also been used as a detonator for a very long time until the azides came along, which we will see later. Mercury fulminate was made from obviously mercury and nitric acid in a very dangerous process. You can see here how it was done industrially. None of these reactors are larger than 20 liters, for the simple reason that if then one exploded, it was only 20 liters, and it would only kill maybe one or two people, and not the whole plant would go up in flames, because these are very dangerous compounds. They are capable of detonation, so of the high explosive energy release, very fast, but they are also very sensitive. So you don't want to use a lot of this stuff, and in fact, as little as possible. Here we see an example. This is mercury fulminate with a flame. Almost no confinement. You see a rapid flash. It didn't have time to transition to detonation. We will see the same compound now in a small test tube. So not a lot of confinement, and it's not a lot of compound either, maybe 10, 20 milligrams. Just a little bit of confinement, enough for it to transition to detonation, which we will see here. You hear it, you see it. This was a deflagration to detonation transfer or progress. So a peculiar property of these primary explosives. Mercury fulminate is no longer in use because it's, well, first of all, very sensitive, too sensitive for modern use, but also, obviously, it's highly toxic. Not just the compound itself, but also its byproduct, namely mercury. But let's go back to nitroglycerin. So at that moment in time, Alfred Nobel had made sure it could be reliably initiated. It was very useful, but there were still concerns about safety. Remember what I said, pure nitroglycerin is relatively insensitive, relatively I should say, but impure isn't. And since it's a liquid, it easily leaks. It's not a very pleasant material to work with, being a liquid. It's nicely demonstrated also here. What you see here is a nitroglycerin plant where a so-called angel buggy is at work. So at some point, an operator has to move the nitroglycerin from the plant for further progress. This was so dangerous. It was done by one person in a sort of wheelbarrow that he had to roll around. He was always alone on a road where there were no people or any other pieces of plant equipment nearby in case he would explode. So you can imagine this man isn't happy. And does he look happy? He does not look happy. Nitroglycerin was and is a relatively dangerous compound to work with, especially in pure form. We can see here, by the way, a beautiful still of a nitroglycerin factory of Nobel somewhere outside of Stockholm. In fact, it should be noted that Alfred Nobel actually lost his brother Emil to an explosion of a nitroglycerin plant. So he surely made his sacrifices. Then came his second invention. So Alfred Nobel, until then, had made the discovery or the invention of the detonator, making nitroglycerin useful as a blasting compound, but still dangerous. His true breakthrough and the start of his huge empire was a means to stabilize nitroglycerin itself. And to do that, he used an absorbent. He absorbed this liquid into kieselguhr, which is a kind of inert carrier, making a kneadable. So you could almost knead it. You could make it into shapes and in the kind of paste. This is, of course, the very well known dynamite. He would then wrap this in paper, and this would be a full useful explosive device. Detonator would be inside. You can see a depiction here, cut in half. This is the dynamite, a kind of paste almost with nitroglycerin in there, detonator, and a fuse on the outside. And this was a very handy, very useful way to use for the first time high explosives in a very reliable and relatively safe way. I say relatively safe, it's still nitroglycerin. Dynamite has the unfortunate property that it sweats. If it stays, especially at high temperature or for a very long time, nitroglycerin will slowly start to separate from the kieselguhr and escape from its package, which, as you can imagine, is very unfortunate. But this did totally revolutionize the world, not just in terms of warfare, but also in terms of mining, of civil applications, because before that, gunpowder was the only way to really do civil blasting, like mining and so on. With this, you could do much, much more for very cheap as well. So very quickly, black powder became obsolete for blasting, not for guns. It stayed useful for guns for quite a long time, as we will see later. But dynamite truly revolutionized the explosive world. For the first time, humankind could harness the high explosives, the really powerful version. Meanwhile, a man called Schoenbein, a teacher originally, later on a professor, made a discovery in his kitchen. He had the tendency to not leave his work at the university, but continue in the confines of his own home. In his kitchen, he would do chemistry experiments involving strong, dangerous acids to the dismay of his wife. And one fateful day, he had accidentally spilled a mixture of nitric and sulfuric acid onto his wife's cotton apron. To hide this fact that he had stained it, he tried to dry it on a heater, and noticed that it at some point spontaneously caught fire, burning without any residue of smoke, which he found, of course, very interesting. He then went on to investigate further, and he actually discovered that you could nitrate cotton or cellulose. This is the man right here. You can see his implements of the trade in the back. He had discovered nitrocellulose. Cellulose, as you know, is a plant-like material. It's easily found, can be made from wood and so forth. It can be nitrated. Actually, has a lot of hydroxy groups. You can see here. It can be nitrated to several forms. You obtain a white powder that's actually almost indistinguishable from normal cotton. If you would nitrate a piece of paper, for example, after nitration, if it's done correctly, it will still look the same. So it still has the outlook and feel of normal cotton. At the beginning, Schönbein was really very enthusiastic. He thought this is going to be a great discovery. I'm going to make a lot of money on it, perhaps in a similar trend as Alfred. But unfortunately, because the properties looked at first glance, the properties looked great. There are no solid products, and not like with gunpowder, for example. You don't have this nasty smoke that also clogs barrels, that corrodes, and so forth. It also seemed to be much stronger than gunpowder. But after he sold the patent and the first manufacturing plant started going, it immediately went pretty bad. It exploded, and it was attempted several times, but the industry just kept being plagued by unfortunate accidents, taking the lives of many people. And at some point, the interest in nitrocellulose simply declined. It was deemed too unsafe to use. Here we can see nitrocellulose. As you can see, super quick combustion, no smoke, clearly a low explosive. It deflagrates. But as said before, unfortunately, deemed too unsafe to use. However, chemists being chemists didn't leave it at that, and a man called Abel started to investigate, and he found actually that the reason why the nitrocellulose was so unstable was not because of its intrinsic properties, but because the manufacturing process was just bad, especially the washing. Nitrocellulose becomes unstable if there is traces of acid present. And since it's made from a mixture of strong acid, that means that if you don't wash it very, very thoroughly afterwards, you will have always traces of acid in it, which will destabilize, and at some point destabilize enough that it can combust very easily. It is not so trivial to just wash it because the cellulose is usually pulp, and it's not so easy to really get and rinse it very properly. But Abel invented a process that was also easily scalable, that really improved the way that the pulp was washed. And this process was further improved later in the early 20th century by Thomson, and produced the first real useful nitrocellulose, a stable and very powerful material. However, we're still not there. It was still not replacing gunpowder at that time. The reason was it was too powerful. It was too fast. Nitrocellulose, being derived from cellulose, kept the texture of cellulose, which is relatively porous. It's too fast. When you ignite it, it burns so fast that traditional guns would simply explode. It wouldn't have good ballistic properties. You could go and work with collodion, which is a lower nitrated form, but that was too irregular, and that would cause also bad ballistic properties. It took until almost the end of the 19th century for the first smokeless powder to be made. Smokeless powder, again, we see Nobel being on the scene here, but he was certainly not the only one. Abel was also there, and also some French scientists. They basically dissolved the nitrocellulose, or partially dissolved it, using a solvent. And you would make a sort of plastic, almost plastic paste that you could extrude. And this was interesting because if you could extrude it, it would no longer be porous. It would be like a hard material. It would basically extrude like spaghetti almost. Like if you have Play-Doh, like my daughter has, you push it through, you have these long strings, it could then be cut to appropriate sizes, which is really, really good, because that is something you need if you want to have good ballistic properties. Depending on the gun, but depending on the caliber, you would require different size, different burning rates, which could be done now. One could extrude this powder as a kind of spaghetti, and you could cut it to the desired length. It was then also discovered that this was far superior to gunpowder. It caused less fouling. It was much more powerful. This was the future. You can see here how it looks. And this is the invention that would go into the First World War, namely cordite. Cordite is also a form of smokeless powder where one also adds Vaseline. The Vaseline stabilizes the further stabilizes the nitrocellulose composition and also reduces the burning rate somewhat, resulting in better ballistic properties. This is actually a bullet, a British 303 round, as you can see here. The cordite actually, and here you can see very clearly, this is how the bullet was filled, not with the kind of fine grains, but with almost spaghetti-like pieces. This was the cordite. And the reason why it's in such shape is to slow the burning rate down sufficiently to have a good bullet without exploding the gun, basically. And here we see a old manufacturing plant where they are basically nitrating wood pulp. And this is an extruder. You can see the spaghetti-like cordite coming out, ready to be cut into appropriate size. Nitrocellulose was invented just in time for one of the great upsetting events in history, namely World War I. In World War I, high explosives were used for the first time on a grand scale. And of course, one of the most prolific uses was in shells. Shells, high explosive ammunition. World War I was kind of, let's say, symbolized by a discrepancy between the old and the new. On the one hand, we had a lot of new technological advances in warfare, the high explosives, weapons like shells, where you basically have, you can compare it to an enormous bullet that propels not just a inert metal bullet, but actually a projectile filled with high explosives that explodes upon impact. Which is, of course, an extremely powerful weapon. We also had new and advanced guns like machine guns, and of course, not to be underestimated, mass production. Not only did we have these advanced weapons, we could produce them en masse. The tactics, on the other hand, were lagging behind. Remember these massive charges into machine gun fire, trench warfare, and so on. We had a big discrepancy between the tactics and the technology, resulting in, of course, massive loss of life. High explosives were a very important part of World War I. They wreaked havoc. Fortresses that were previously determined to be impenetrable were destroyed within days using high explosive artillery and ordnance. And they were really almost a revelation in warfare. Also interesting that actually these weapons of war were made by the gentle hands of women. What you can see here is a munition factory in the UK during World War I. Since all the men or all capable men were at the front, there was an acute lack of workers in the plants to make all these mass-produced powerful weapons. And so the duty came to the women who were actually usually working in these plants, producing the weapons that would be propelled by their husbands and brothers and fathers. Among these new high explosives that were used in World War I, dynamite was not really one of them. Dynamite is actually a little bit too sensitive even to be used in warfare. If you try to shoot it using artillery, it would probably explode in the barrel simply due to the shock of being propelled. There was a need for new explosives. One of those explosives that filled the gap was picric acid. I think everybody probably has heard of this very beautiful solid. It has a beautiful yellow crystal, some of the most beautiful crystals you will have ever seen. It's relatively powerful. It was actually discovered a long time ago and uses a very powerful yellow dye. It stains everything completely canary yellow, including your skin, which will need to be washed, which you can't even wash off. Your skin really needs to come off by itself before you can use the yellow color. Sprengel, however, a German scientist, discovered in 1871 that this dye also had high explosive properties. The reason why it took so long is because picric acid is actually quite unsensitive. I mean, you need a detonator or a very strong shock to set it off, which is one of the reasons why it was very useful to be used in shells and as artillery. It was called lyddite in the UK, for example, or much more beautiful in German would be Granatfüllung 88. That is as scary as it sounds. So picric acid was very useful. but it had some unfortunate properties. The first being is very toxic. So using it, producing it was not the most pleasant of things. But perhaps even more concerning, it's a strong acid. As every chemist will see from the structure, it's a phenol with a lot of electron withdrawing groups. It's extremely acidic, which means it gave corrosion problems. That would be unfortunate, but even more unfortunate is that this corrosion caused the formation of metal picrates, the products of this corrosion, which are extremely sensitive primary explosives. So you can imagine that a insensitive explosive that has the capacity to create its own primary explosive, in a sense, its own detonator over time by corrosion, is not a very pleasant compound. It's cheap to produce, though. It can be easily made from phenol, which is a commodity chemical available in bulk. You have to sulfonate it a little bit, and then our traditional nitration to make our beautiful yellow crystals. Can also still be found in some labs of the past, because it's also very useful to crystallize some organic compounds. Um, the picric acid is the first explosive. It was actually not used for a very long time because of these unfortunate properties of being acidic and very toxic. And nevertheless, it's very interesting from a historical point of view. We then move on, of course, to the other grandfather of explosives, which is trinitrotoluene, or TNT. I guess everybody has heard of this. I think if anybody mentions explosives to a layman, TNT is the first thing that comes to mind. And there are probably, incredible amount of misconceptions about TNT. The first being that it's very sensitive. It is absolutely not. It's quite insensitive, actually. It's very hard to detonate it. You really need a detonator to detonate it, which of course makes it perfect for use in shelling and artillery. But another very good property of TNT is its low melting point, only 81 degrees, meaning boiling water can melt it. And that makes it interesting from a industry perspective. The reason being, you could melt and cast this. Up until now, the other explosives like picric acid, you can't melt it, because when you try to melt it, it will explode or at least degrade. So actually, if you wanted to fill a shell with picric acid, you had to literally stomp it down using a broomstick or something and fill the shell, stomping it down until your shell was full. Not so with TNT. With TNT, you could melt it beforehand safely and then pour it into a shell, like filling a glass of water. That made it, of course, much easier and much faster to fill these weapons. So also on the read about TNT is still in use. It's also a very stable explosive. It's not acidic. It's actually a very stable, a workhorse of the military. Still to this day, TNT is used a lot in all sorts of military applications. Like some of its compatriots, high explosives, it was also discovered long before it was known to be an explosive. Only in 1891, it was truly recognized that this was a powerful and very useful explosive. It's made, again, from a commodity chemical, toluene, which you can get from crude oil in a three-step nitration, which is, it seems complicated, but on industrial scale, it's very cheap to do this, and you can make your compound relatively quickly. Again, we see here the ladies filling up the shells with TNT. Also interesting, perhaps, for the chemists among us who think flow chemistry is a very innovative thing. I should mention that nitrotoluene has been produced in flow since World War II. Since World War One already, between World War One and World War Two, because the process is not without risk. To improve the safety qualities, it's produced continuously, meaning it's not a single reactor. It's basically being pumped out continuously as it goes. Now, TNT, how powerful is it really? I'll give you an idea. So this is 5 kilograms TNT in a hopefully old car. You see the explosion, very, very powerful, this explosive. And we see 50 kilograms TNT because why not in a house? A couple of things that you might have noticed, the brisons. You see it's ripping apart whichever container it is in, whether it's a car or a house. You saw the house rips to shreds. You saw the car rip to shreds as well. Typical behavior for a high explosive. And also notice, especially with the house, almost no fire, and the smoke is only coming from the other items that are present in the confinement. So typical for a high explosive. some lag. Um, Another important one is ammonium nitrate. I think ammonium nitrate now also has the eye of the public for many reasons. One being probably, of course, our not so good friend Anders Breivik and his attack. It's used by terrorists quite often. But also because of the disaster in Beirut, of course. This is a commodity chemical, a very important fertilizer, very, very important, produced on tons and tons and tons scale annually. It's actually, as a explosive, it's not that great, actually. It's hygroscopic, meaning it picks up water from the air, rendering it inert, which is very a nice property to have for an explosive. It's not very powerful. It's actually almost barely a high explosive. But, and this is the most important thing, it's first of all very insensitive, which is good, but it's especially incredibly, incredibly cheap. Um, you can get kilos and kilos of it for only a couple of euros. So it's on bulk, of course. So it was used very often in war to dilute basically other more valuable explosives, especially near the end of the war when TNT, picric acid, and so on became in short supply. It would be used to complement the explosives, being added as a kind of filler that still had some power instead of adding an inert filler. It is almost always used as a mixture, never pure. A typical one, for example, is amatol, where it's mixed with TNT, molten, to create a kind of adulterated TNT that's still powerful enough for most applications, but much cheaper than pure TNT. But you have a whole slew of other compositions as well, like ammonal with aluminium powder, schneiderite asphalt with nitromethane, and so forth. Sorry, hydrazine, and so forth. Kinipak with nitromethane, and so forth. And of course, ANFO, which is relatively recent, where you simply add a fuel like diesel, a very low power explosive, not used in the military, but still used a lot for civil blasting to this day. The reason for that being, again, cheap. It's extremely cheap. You can literally get ammonium nitrate explosives by the truckload. And new recent innovations make kind of slurries out of it, viscous slurries that are perfect to put, for example, in a drill hole. You can just fill it up with explosive, with ammonium nitrate explosive. Not very powerful, but plentiful. So that is why it's also, again, to this day, used a lot, especially in the civil industry for explosives. Unfortunately, it's also known for its industrial accidents. I think everybody remembers the explosion in Beirut. That was ammonium nitrate stored. I said it's very insensitive. That is definitely true from military perspective. But if you would expose it to very high temperatures, like say a large fire in a confined environment for a very long time, at some point it will start decomposing, which can lead to a chain reaction, which will lead eventually to a detonation, which is also what happened in Texas in 2013 in a fertilizer storage, where about 7.5 to 10 tons exploded. You can see here the fire and the detonation. 7.5 tons of ammonium nitrate. God Almighty, indeed. So we see here the danger of this well, common fertilizer. Let's say. Very good. We're moving on to the Second World War, another age of destruction. And here, again, high explosives played an important role as the science of this explosive was refined even more. There was a need for it as well. What was needed were explosives that had higher velocities, detonation, higher power, and especially there was a need for anti-tank weapons, especially infantry portable anti-tank weapons. Tanks were becoming more important and they needed a way to destroy them by a single foot soldier, for example. And again, explosives came to the rescue. Also improved manufacturing methods, allowing explosives that previously were just an oddity to be produced on larger scale were very important. And the theoretical models not to be forgotten, like Seldowitz-Neumann-Döring theory, which allowed the design of new weapons, of which you will see one later. And not to forget, because a physicist always likes to brag about their nuclear weapons, but chemical explosives play a vital role in nuclear weapons. And in fact, you can see a kind of implosion type nuclear bomb, a very powerful version, is only possible thanks to a very complicated and theoretically not so trivial formation of these explosive lenses. So actually, This fissile material in the center is actually surrounded by highly complicated, very technologically advanced explosives configuration. So to make a nuclear bomb, you need chemical explosives to get your compression of your fissile material up to the critical mass. So again, there, explosives played an important role also in the Manhattan Project. The first innovation would be lead azide. There was a need to replace mercury fulminate. Mercury fulminate was capricious, it was a bit sensitive, but especially it was very toxic. And also when it exploded, it gave contamination, which may sound strange, but that people would care about it, but people did. The mercury, not very interesting. Luckily here, at around 1891, Curtius discovered that if you made the azide salt of lead, you got a very good initiating explosive. Lead azide is powerful, more powerful than mercury fulminate, for example, but much less sensitive. Um, Especially if you dextrinate it, meaning you add dextrose to it. It's a kind of phlegmatizing almost. Not much, a little bit to make the powder free flowing, but much less sensitive. So this had a very strong, a very good efficiency of initiation, meaning you don't need a lot to initiate the common high explosives. It's very storage stable, which is very good. It's also very cheap, which is of course of vital importance. It is, for that reason, still widely used today, although it's also falling out of favor because it still contains this very unfortunate lead, which is of course not very interesting from an environmental perspective. And if you're wondering, yes, there are environmental concerns with high explosives. As you are shelling your opponent, it's good to think about the environment that you later want to conquer, I suppose. The synthesis, of course, is extremely easy. I guess anybody with a basic chemistry knowledge background will realize it can be simply made from a precipitation reaction between sodium azide and a lead salt, because lead azide isn't water soluble, so it will simply precipitate from solution and is made to this day in that way. Another extremely important explosive that only really got traction in World War II is RDX, Research Department Explosive. This white solid, white crystalline solid, is a very powerful explosive. It's much more powerful than TNT. It's also relatively insensitive. You need to make a strong effort to get it to detonate. It was discovered already before World War I, but it took a while for a good manufacturing process to be in place to manufacture this reliably on large scale, which is the reason why it wasn't used in World War I. It's often used as a mixture, for example, Composition B or Comp B, used a lot in World War I with TNT. The reason being it's melt castable. It's stronger than pure TNT, but you can still fill up your shells with it easily. Torpex was also used, where it was used with TNT and aluminium, very powerful mixture. And of course, C4, how could I forget? I guess very prevalent in movies and video games worldwide, where it's mixed with a plasticizer like polyisobutylene, making a kind of kneadable mass that you can adapt to your needs on the fly. You can see it here, typical C4 block, aerial bombs, and so forth. It is still one of the most widely used explosives today. For sure in any military worldwide. The mechanism is relatively complicated. The synthesis itself is relatively simple. One starts from hexamine, which can be made from ammonia and formaldehyde, and one simply nitrates it in a rather, operationally complex procedure to get, after some cleavage reactions, the RDX, which is a very beautiful symmetrical molecule, as you can see. So RDX is extremely important even to this day as a military explosive. The second one, or the third one, is PETN, which is an important nitroester. It looks perhaps at first glance a little bit nitroglycerin, although not quite. It's also very powerful as RDX. It's a little bit more sensitive, but one of its great advantages, it's very easy to initiate. So while it's not so sensitive to friction or impact, which is bad, it's very sensitive to initiation by a detonator. So it's the perfect booster explosive. And it's also used for that purpose relatively often. Also, again, to this day. It's also used sometimes in mixtures. Semtex, for example, another Hollywood favorite, where it's mixed with RDX and a plasticizer. So you have a kneadable mass. Semtex is a little bit more powerful than C4 and especially easier to initiate. And one of the reasons also why it got a kind of bad name is because in the beginning when it was made, it was almost undetectable because it had no volatile compounds. At some point, Czech Republic, where Semtex was made, was forced by other governments to include on purpose a small amount of a volatile, easy to detect tagant, as they call it, into the procedure, into the manufacturing process of Semtex to make it more easily detected at airports and so forth. It's used a lot in different applications like detonation core, detonation sheet, as you can see here, all tools for the demolition man to make it a bit more easy. Again, since this is very straightforward, a simple Cannizzaro reaction between ethanol, so acetaldehyde and formaldehyde, making pentaerythritol, which will then nitrate into pentaerythritol tetranitrate, which is a white salt, the explosive that we have been talking about. So PETN, also an important explosive. HMX then was actually not used during World War II. It was known already actually before World War II, but it was considered to be an impurity of RDX. It's made if the conditions are not perfect. It was much more powerful than RDX, but also much more sensitive, so it wasn't really a desired compound to have. But it gained a lot of attention lately, actually, after World War II, in the 80s, 70s, because new technology arose that could be used to make it less sensitive. And therefore, you could still use the incredibly strong power of HMX, but still have the low sensitivity. And it's actually now being used in some of the most advanced warheads in current day military. So HMX, also an interesting molecule, beautifully symmetric, as you can see. Going forwards, we have the anti-tank weapons. This is a beautiful example, in my opinion, of the marriage or the intertwining of physics and chemistry, using the physics of shockwave theory and the chemistry of explosives to make a new sort of weapon with peculiar properties. Here we see a tank hit by a Panzerfaust, a armor-piercing, an explosive anti-tank round. You see this peculiar hole that was made. So the Panzerfaust is basically an explosive weapon that made use of the shaped charge, or the Monroe-Neumann effect. We will see the physics behind it later, but what it basically does is this focuses the explosive energy into a very small area, allowing it to penetrate into even heavily fortified targets. Shaped charges are something that were discovered by Monroe in the States and Neumann in Germany almost at the same time. What they discovered was this: if you have an explosive, a high explosive, you put it on a metal plate and you detonate it, most of the energy is directed away from the heavy metal mass. This is also known as the Misonnet-Chardin effect. This was known because it's looking for the way of least resistance. However, Monroe noticed if you make a cavity in the explosive, above where the target in this case is, he saw deeper penetration into the target, which was strange because in the end you're using less explosive. Actually, you're making a hole in the explosive, removing explosive, yet producing a stronger effect in the target right beneath it. The reason behind that is actually that there is a physical effect at play. He also noticed that if you then would not just leave it a bare explosive, but you would actually put in a liner, it's called, so a piece of metal, for example, to cover this hole on the inside, the effect is even stronger. So what's happening here? In fact, the shock waves, you ignite or you detonate the explosive on the top, the shockwave passes through the material, compresses, the shockwaves meet actually in the center, in this cavity, and they reinforce each other, sending out, compressing the liner in this case, and sending it out like a kind of spear, a jet and a slug, as it's called. The velocities of these jets are incredibly high, up to 10,000 meters per second. That's extreme. At such speeds, they create so much energy in such a small area that metal acts almost like a liquid. And that's why we get these deep penetrating effects. They also note that if you then have a standoff, so you take the explosive a little bit away from the surface, you can even get deeper. That's of course because you give the jets more time to form. So this is a shaped charge effect. It's actually the two shock waves colliding inside this hollow, squirting out a jet of pure metal in this case. Of course, as soon as it was discovered, it was immediately weaponized to make anti-tank weapons. You can see here clearly, this is the Panzerfaust. You can see clearly this hollow shape, and this is actually just a hollow dud, just a spacer. You can see clearly, again, the shaped charge form here, of course, meant to penetrate, cause a jet to form and penetrate a tank. The RPG, of course, also very well known. Again, you see here this kind of conical form of an explosive. Nowadays, you also see it sometimes or hear from it as the EFP, an explosive form penetrator, in war zones like Iraq, where they actually take it one step back and they make the liner a bit more shallow, but using it to propel it almost like a semi-molten slug of metal, which can be projected over larger distances like 20, 30 meters. It's useful to, for example, destroy armored vehicles from a short distance, like this American Humvee. However, it's not all death and destruction, because shaped charges were also used for more scientific purposes, like you can see here. This is the Hayabusa 2, a recent, a satellite that was meant to investigate the Ryugu meteor or space object. It wanted to make a hole in the meteor to get a sample of the interior. And to do that, it used actually a shaped charge of about 2 kilograms with a copper liner. And it used HMX as the explosive. So it's not all death and destruction. Here we can see a shaped charge in action. It's right here, very small. This is a vault door made from metal, of course. You will see it detonate. And you saw how fast this jet is shooting simply straight through this vault door as if it wasn't there into this barrel of water. And the speed is incredible. You can see it so fast, the water, the objects around don't even have a chance to react. Their inertia is too big. That's how fast this jet is being projected. Even the shockwave is running behind. You see then afterwards, suddenly everything starts to move, but the jet has already done its grim business. Very good. Moving on to the future. Obviously, explosive chemistry is a science, and like any science, it doesn't stop. It just keeps going. Of course, also in the new battlefields of today and tomorrow, the requirements are a little bit different. However, we are still looking for high power. We're looking for high density. The reason for that is high density means you can pack more explosive in a smaller space, like a missile, which obviously is nice. But very important nowadays, it needs to have a low sensitivity. The military is very wary due to past experiences of their own munitions detonating or exploding, for example, because of being hit by an enemy attack or due to sheer chance. So it's very important that the munitions of the future are very low sensitive and only explode when needed. So they need to be low sensitive, but they also need to be able to be reliably exploded when needed. So this is a kind of a tall order, right? What's also important is, the green wave hits everybody, including explosive scientists. It needs to be a bit more environmentally free, so no lead and so forth. There are some specialized functions that are required, like agent defeat weapons, which are particularly meant to destroy, for example, biological weapons. They will contain, for example, fluoride in the explosive molecule to generate fluorine during the explosion to destroy biological entities. Of course, the chemists, seeing all this, will rise to the challenge with a new slew of powerful molecules. The first and perhaps most important one is hexanitroisoazavircitane, which is a very, in terms of explosives, a very recent discovery. It's as old as I am, also known as CL20. It's a white solid. It's very powerful. Up until relatively recently, the most powerful non-commercial explosive. You can see here the difference between a shaped charge with 30 grams of HMX, the most powerful explosive known up until then, and the same amount of HNIW, and you can see that it penetrates much further for the same amount of explosive. This is a powerful explosive. The only problem, while it's not being adopted much more, is the synthesis is relatively complex. It's a multi-step synthesis. This is only one of them. There are others. And the price is high. It's about €1,000 per kilogram, which is prohibitively expensive for military explosive because you need tons of it. You can't afford to have an explosive that's expensive. So there's a lot of work being done now on pushing down the price of this material. At the moment, there are some companies that produce it commercially, so it is ongoing, but it's still relatively exotic. It's only used for a few very special applications. But it's expected in the future this would be one of the explosives of the future. TNAS, trinitroazetidine, also an interesting explosive. much more powerful than TNT, but also melt castable. This is a requirement of the army as well. An explosive that could replace TNT, still being melt castable, so you can easily use it to fill shells, but more powerful. And TNAS is up to the challenge. Unfortunately, like the previous one, since this is relatively long, complex, and therefore, again, expensive, which is why it's not being used at the moment until a better process is in place. Another interesting thing, going a bit away from the organic chemistry perhaps, are the metastable intermolecular composites, also known as nanothermites. Basically, it's a very intimate mixture of nanoparticles of a strong oxidant, or an oxidant like iron oxide, and a reactive metal like aluminum. Which termite, I think everybody knows. It's a very strong reaction, a lot of energy being released. It's relatively slow because the particles are big. But here, using modern nanochemistry, they get the particles down so small that the reaction speeds up and could theoretically increase to almost explosive speeds. With the big difference that the energy released here is tremendous. So these are very interesting, also as propellants, for example. At the moment, though, they're not really used. There are some problems. Either they're not sensitive enough, or they're very sensitive, which is of course extremely dangerous. So these are for now only a novelty in literature, but who knows what the future may bring. Then we have a whole slew of fancy new molecules, high energy density materials, as they are called, one looking more exotic than the other, very interesting from a theoretical perspective. But as you may remember, until they can be made very cheaply, it's very unlikely they will be adopted by the military because they may be very good, but if they are very expensive to make, and some of them are extremely expensive to make, they are not very useful to be used as a bulk chemical. One oddity I don't want to deny you is this octanitrocubane, which is as crazy as it looks. It is probably the most powerful chemical explosive known to man to date. The only problem is it is more expensive than gold. The synthesis to make this complex molecule is incredibly long, involving some very exotic chemistry, and meaning that it is actually almost, it's so expensive that it's almost infeasible to make this even on the kilogram scale. There are some ongoing research to make it cheaper, but at the moment, and people have been working on it for quite some years, this has not been achieved yet. In addition, it also has a lot of polymorphs, making it even more complicated. But probably you're looking at the most powerful chemical explosive known to man here. Another interesting development are the insensitive high explosives. Like I said, the military also wants explosives that are extremely insensitive. That can also be used for things like nuclear weapons, because remember, all nuclear weapons, they use chemical explosives. You don't want to use a chemical explosive that if somebody shoots a bullet in it, your nuclear weapon will go off. So there's a need there for very insensitive explosives. TATB, triaminotrinitrobenzene, for example, is such an explosive. It's already commercial since the 1970s, so it's not that new. But it's expensive. But for some niche applications like nuclear weapons or some explosive bolts used in outer space, this still has some uses. It's made in a nitration emanation step. A very stable explosive. You can shoot bullets in it, it won't budge. You really need a strong initiation to get this one to fire off. We have NTO, nitrotetrazolone, also a new explosive, 85, very powerful, also very insensitive. Unfortunately, a little bit expensive, although people are very interested. There's a lot of research ongoing and qualifications ongoing in the military. Unfortunately, most of them are classified. But I think NTO stands a good chance of being used in the future. The synthesis is at least shorter than most other advanced molecules, so I think this may stand a chance. FOX7, beautiful name, beautiful molecule as well. Also very powerful, very insensitive, so it looks like a great contender. Unfortunately, expensive as well. This molecule looks simple, but the synthesis surely is not. Going on to a bit more technology, I'm going over a bit faster here because I see time is unfortunately ticking. But an important new development are the PBXs, the plastic bonded explosives. This is basically you're desensitizing the explosive by mixing it with a plastic, and you're making also in that way a piece of explosive that is easy to mold, that you can extrude, and so forth. So this is very interesting, and a lot of work is being done on this using things like HMX or CL20. So also explosives that are actually in their pure form too sensitive to be used can now be used by making these PBXs out of it. And they load it in things like the Sidewinder rocket, for example. A very, very interesting application. A lot of work is being done on this, mostly because it uses explosives the military already knows very well in terms of stability, and you're just changing the matrix in which it is in. And another important development here is they're using not just inert plastics, but also polymers that are energetic themselves, that actually can contribute to the explosive power instead of just being an inert filler. So a very active, bristling field, the PBX field. This brings us to the last part of this talk, perhaps a bit less beautiful. That is, of course, explosives being used as weapons of terror.
Okay, so we would pause the discussion on that note. We'll continue it on the next session. So I hope that you have taken notes, especially on the history and those classification of explosives and the types of explosives. Okay, so we'll just continue that discussion on the next session. Okay, so thank you for viewing. Thank you for um, trying to understand and having been curious about explosives. And after this video discussion on the next session, I would have my own discussion on explosives. So that will be all. Thank you. And by the time you have seen this, this has already been posted in your LMS dashboard.